So I guess this is the third meeting in a series of kind of describing the basic structure of RAMCloud, what we've built so far, how kind of normal operation works, and we're heading towards, I think, recovery basically, which is probably one of the more complicated pieces of the system. So last time Steve was basically talking about how the internals of a RAMCloud is a data center storage system, and it keeps all the data in DRAM, and we have basically many master servers, and each of the master servers exports their DRAM as a key value store. So RAMCloud collectively is managing thousands of these different masters, which are storing data in DRAM. And most of what he talked about last time is how a single master actually organizes this DRAM and how you get access to the objects and how it basically manages the memory inside the master more than anything else. And there was a diagram similar-ish to this last time, I think. So basically here I have a diagram of what a master looks like, and you have an incoming client write request that says that it wants to put some value in a particular, store a particular value for a particular key in RAMCloud. And really the idea last time was that there was this in-memory log, and you would append the object to the head of this log, and you'd update some entry in the hash table here. So you'd repoint some key here after you insert the object into the log so that later read requests can find it. And there was this part that made it all seem very simple in the last set of talks, which was that there's all this stuff you have to do to organize it, but then we would just kind of send this stuff out to backups. There would be these 3 RPCs, and stuff would be stored durably. But that actually finesses a lot. So today I'm going to be basically diving into just these, more or less, these 3 RPCs, what they're for, how we organize them, how the data is organized. Basically to provide durability. So basically last time, by just kind of putting 3 arrows on the board, he finessed a lot. So we're going to dig into that. So the real goal of RAMCloud's replication is to store data on other nodes in the cluster durably, so that when nodes fail, when we lose this DRAM copy of data, we can reconstitute it. So we'll kind of veer into the territory of recovery here a little bit, off and on throughout this little session, but we'll try and keep it focused on as much as possible on the replication itself. So last time, as I said, Steve said, we kind of send these, whenever we append objects to the head of the in-memory log on a particular master, we send the objects out to a few different backups, and they store it. So, right, so I guess the first thing to kind of go through is basically what are the overall goals of and requirements of the replication mechanism we have. Like, what do we want out of it? That'll give a better sense for why it's organized the way it is. So I kind of have a list here of, the left here is kind of more goals or kind of high-level concepts that need to be handled by this, the replication module that handles the replication on the masters. And then these on the right kind of result in some requirements that we have to meet. So for example, we want durability. Nodes are going to be failing. And we want our data to be stored on disk in a way so that even if nodes are crashing, we still have access to our data and can reconstitute servers using recovery. Got a very quizzical look. Do you have any question? Very skeptical of my talk structure so far, I guess. What's that? That'd be a surprise. Okay, so we want durability. We can't store it in DRAM all the time. We basically need to use disks since we need some kind of non-volatile storage. And in particular, this second point is really what drives that. Maybe there's some hope for using DRAM replication, but the cost of DRAM makes that completely impractical. So to the extent that we can keep it on disk, that's even better. Another requirement is that we really want strong consistency. So we don't acknowledge data unless it's stored non-volatilely. We think that there's a really, really, really high probability we'll be able to deliver that data to you later on future read requests. And we need to deal with the loss of non-volatile data too. So we may end up losing backups over time, and whatever this replica manager does on the masters, it needs to compensate for those kinds of losses. Fast recovery is really the point. In practice, the goal here is to reconstitute servers, and you'll see that the fast component of this actually has a key influence on the way this stuff's structured. Really what we're doing is we're trying to optimize. Well, there's a few different trade-offs we're trying to optimize, but the end goal is to really try to organize this data in a way that we can bring a server back to life in 1 to 2 seconds when a server fails. And we won't get into the specifics of that, but next time, hopefully, that'll be the topic. So that means that a few things. First of all, crashes can happen at any time, so that means that this log data that's being replicated needs to be safe for read and replay at any given moment. The log can't get into some inconsistent state. If we kind of mess up the log in some way because we're in some intermediate step and then we do recovery, that node crashes and we do recovery on that, we'll recover to a corrupted state. So a lot of the complexity in the replica manager centers around trying to do things in ways that won't result in inconsistencies during recovery time. And then the key to getting the very high or very fast recovery is that we want to organize this for very fast read bandwidth. See, that happens basically by striping data across the entire cluster using these segment-sized blocks, so we can use the aggregate disk bandwidth of the entire cluster. And then low latency normal operation is basically a non-negotiable. That has to be there as well. We want append times that are close to about 1 RTT additional time. So if we have reads of 5 microseconds, ideally we would have writes of 10 microseconds. In practice, we're not getting nearly as close to that as we'd hope, but hopefully that's just a matter of engineering and not anything. It shouldn't be anything fundamental. Basically, you see here there's an RPC here and then 3 parallel RPCs. The hope is that you can return to the client once this has been acknowledged. So should be able to do it in about 2 RTT time, about double what our read time is, basically. And then that also implies that we never want to exhibit disk latency, which means we have to do some scheming to figure out how we're going to avoid synchronous disk writes, which I'll talk about in a moment. Another important aspect is that eventually we do want multiple master threads. We do support that to some degree now, although it hasn't been well tested. But basically, if we have multiple master threads performing these writes at the same time to the head of the log, we want to be able to batch those writes and send them out to the backups in a batched way, so that basically we can have multiple concurrent appends happening to the head of the log at any given moment to provide higher throughput. And then scalability is really a key consideration as well. So remember, RAMCloud is supposed to operate at scale of, say, 10,000 masters. And so that means if the masters are doing any centralized operations, then that's going to limit the scalability we can get up to. So we want the masters to operate almost completely independently at all times, and that has an impact on how we organize the log and how we track, in particular, the segments, which I'll talk about in a little bit. And yeah, and the last thing is basically, it's basically tied to that. We really don't, we want to be able to make kind of these allocation and cleaning policy decisions independently of the underlying way we replicate things. So last time, Steve spent a lot of time talking about garbage collection and how we decide which DRAM we use and which DRAM we reuse and all of that. So all of that is hidden from this module. You can forget about all that crazy stuff that Steve talked about last time. And in the end, that really means that maybe the key constraint for the scalability is that basically we can't really consult any centralized authority on where we place segments in order for this to be scalable. Okay, so that's kind of the high-level overview of the goals of this system. So more or less, this diagram already kind of sketches the basic, gives kind of the starting point for entering this conversation, I guess. So the first trick that I think is important with replication that's important to realize is that to get the low latency operation, we do a pretty simple trick, which Steve already mentioned, which is that basically when a master, so last time we described the master's log is segmented. So this log is basically broken up into 8 megabyte chunks. And then the most recent 8 megabyte chunk is what we call the head segment in the log. And that's actually, that particular segment is being buffered on 3 different backups in the cluster who have 8 megabytes of data in DRAM, which they're using to basically replicate identically the head segment on that in the master's log. And so the key is that we don't want to take the synchronous disk write. So what we do is we have battery backups on each of the backups. And since we're only buffering, say, 8 megabytes from the head of a master's log, it's not that much. We can flush that out to disk in a few hundred, not even a few hundred milliseconds, about 100 milliseconds or something. So so that's plenty of time. Things like Facebook servers generally have like 45 seconds of battery backup, and there are other ways you can get non-volatile storage on the backup. So we also want to limit that to some extent because it's expensive, and to the extent that we can get it on disk, that's a safer bet anyway, so we'd like to get it on disk. But that gives us, basically, keeping this stuff in non-volatile memory allows us to buffer updates when a client request comes in and reply to them and say that we've got your data, we'll be able to recover it even if there's a power failure or even if one of these nodes crashes. So does that all make sense? So that's the kind of the first trick, I guess. So we call this buffered logging, I guess, which is our approach to getting disk-like DRAM-like performance while kind of having the redundancy and durability of DRAM. Sure.
So how much of the memory of backups do you think are being consumed when you want to write this amount of data on the disk? For example, if like 50% of memory is being used for backing up other
exactly, right.
masters data, you probably won't have
right.
batteries.
So actually, so the way this works out, mathematically this works out kind of nice because basically every master in the cluster only has one open head segment, but they also are acting as a backup. So that means that in expectation across the cluster, and we'll get into more about how we scatter segments and stuff, but basically you expect that each master has about 3 replicas that it's accepting data for in the cluster, right? So if you imagine this master is acting as a backup, and some of the other masters in the cluster are actually sending it replica data, if you kind of spread those evenly across the cluster, you expect each individual master really is only accepting data from 3 other masters at any given moment. So it's actually only 8 times 3, right? It's 24 megabytes. That's a bit of a fib in the sense that you'll see during recovery we actually need more non-volatile buffer space in order to recover quickly, basically to make it so that we don't need to do write I/O on our devices at the same time we need to do read I/O. So basically, during recovery, you need to do a lot of reads really fast, and you'd like to defer the writes. And one way to do that is to basically non-volatilely buffer those. So to the extent that you can have more, it helps. But it's even still then it's limited to things like an order of a gigabyte rather than things like 50% of memory size or anything like that. Okay. All right. So let's see. Maybe I think I'll just, before I dig into each of the topics, I'll just give a sketch of some of the. Maybe I'll just kind of spill the beans and tell you what the whole story is, more or less. So basically, and then I'll kind of go into each of the topics in detail. So basically, the way we get the way we really organize this for fast recovery is that masters actually, as they're adding data to their in-memory log, are actually scattering these replicas across all of the backups in the cluster. So a particular master's log is actually scattered all over the entire cluster. And the goal of that, the idea behind that is that basically when a node crashes, we can read from all of those disks in parallel. Each of the disks is only reading a very small fraction of the crash master's log, but we can use the entire aggregate disk bandwidth at once. So that's kind of the key, the linchpin piece in making fast recovery happen is that we basically need really, really high aggregate disk bandwidth. And so you'll see that one of the keys to this is scattering segments around. And then once we get through that part, I will basically talk to you about how we use the logs for recovery, and then how we deal with loss of replicas, replicas that are corrupted, inconsistent replicas. Basically, what happens when the log gets damaged? How do we make sure that we don't recover to an inconsistent state in that case? And the last topic, hopefully we'll have time for, is basically, last time Steve talked about log cleaning, and the log cleaner actually cleans space in memory, and you remember there's this kind of memory compactor and then a disk cleaner as well. And so there needs to be some interface to the backups to tell them to free space, to really basically release segments. And so if I have time, I'll talk about that and some of the failure scenarios that can get into that and how we make sure we don't leave garbage around on our disks or inadvertently delete replicas that we might need later on. Okay. All right, so see where we're at here. So I guess I don't know if I haven't defined anything well, just let me know. Like if I need to say more about what segments are, etc. Mostly this will be simpler than Steve's talk in the sense that you can forget about a lot of what he said. Things like seglets. Those to me, those are helpful. Those are like a really important thing. But from the perspective of the replica manager, you can basically ignore them, which is great, because it makes understanding this a lot simpler. All right, so I'll describe the interface here, which may or may not be helpful. But so basically, there's a function called alloc_head in a class called replica manager. That each master has an instance of this replica manager, which is responsible for generating all these RPCs and maintaining the durability of each of these replicas. And remember last time he said that you have these 8 megabyte DRAM segments. They're non-contiguous, but you get to ignore that for the sake of this talk. And what happens is when the log cleaner decides it wants to add new data to the head of its log, it's basically run out of space, and now it has this new blank 8 megabyte region of DRAM. It registers it with the replica manager using alloc head. It just passes in that segment, a pointer to that segment.
You said log cleaner, did you mean object manager?
Yeah, exactly, sorry.
Right.
Right, when an object manager basically is running out of room in that head segment, it needs more space. So it's going to tack on a blank new 8 megabyte segment to the head of the log. And this just notifies the replica manager, hey, this is where the next chunk of data is going to go from the log. And then there's a method called sync, which takes a segment and an offset. This basically notifies the replica manager, hey, for that segment that I told you about before, this is how much of it has valid data in it so far. So you should try to replicate up through that offset. So this blocks until the data's been replicated up through that offset. So you'll see the master basically appends data to the log, calls sync on that offset, and then once that's finished, this call will return, and the master can then acknowledge data to the client. There's the free, which basically tells the replica manager it's safe to send out an RPC notifying the backup so that it can discard a certain set of replicas. And the last thing is basically for recovery. We'll get into it briefly today. I call it find replicas for log. And this basically gives you, for a particular server that left behind a set of replicas, it finds them all. It just gets you a list of them all in one place. And then there are ways to validate whether or not you have the complete set, etc. Okay, so I guess we've kind of already walked through a write operation. Let me diagram it in a slightly different way so I can kind of show you how it deals with concurrency and things like that. So the way I usually visualize this is basically if you imagine the master has its log, and let's say it has a couple objects in it. I'm just going to label them really naively for now, so we'll call them A and B. And then you can imagine the buffer on 3 other backups in the cluster. So these buffers, let's say, at the moment match. So everything's up to date with this particular segment. And don't worry too much. We'll talk about segments for a little bit here, but we'll talk later about how you organize segments into a full log. For now, let's just focus on replicating a segment. Okay, so you can imagine a client request comes in and says something like, I want to add a value to the log, right? And so what happens is the master will just copy this into its in-memory log. And then it will call the same thread, so this will happen pretty quickly, so it gets a return. And what it'll do is it'll call sync up through the offset that the C got written to. This is probably more called append, actually, probably a better name. So it'll sync up through C, say. And then what happens is this effectively blocks this thread. So it starts to wait for C to be replicated to the other nodes in the cluster. And so control basically passes to the replica manager, and it begins to shoot out RPCs to the other nodes in the cluster. That's right. So that's the append is actually on the segment. So you append an object to your segment. See, this is a segment here. And then the sync basically tells the underlying replica manager, hey, I've added some data to this, and I need it replicated up through this particular offset. So the methods are on 2 different objects, kind of weirdly, but yeah, it used to not be that way. It used to be the way you described, but then we realized there was no need for the replica manager to know that the data was even added to the segment until yes, exactly. Yep, there's a buffer that's shared by both of them. Basically, the replica manager can see that buffer, and the master can see that. The log code can see that buffer. Yeah.
And during the sync, are you sending all the data in the segment, or are you only sending C?
That's what I was about to get to. So, and the answer is neither of those 2 options, but close. Yeah. So you send a lot. Basically, you send as much as you can. Up to some limit. We don't want to go nuts, so we don't want to send 8 megabytes in a shot. So if there's, say, more than that, we might make the RPC smaller. So the way I was going to illustrate this, basically, but you've already kind of copied on it, is imagine like a call comes in for like We'll call it append, just to be consistent with the new terminology. So you have an append D, that kind of tacks some chunk on. And let's kind of imagine there's a concurrent operation going on that's also like append E. And let's say they immediately turn around. Each of these are two separate master threads appending objects concurrently. Well, they'll get ordered somehow in the master's log. And they'll both call sync at the same time. So two threads are blocked on sync. One is synced up to here in the log, and one is synced up to here. So basically, nothing will happen immediately if the other sync for C is still outstanding. So that is, if the RPC hasn't come back for C yet, it won't send out a second set of RPCs to the backups. It will wait until basically each of those backups is done replicating the last replication operation. And once that happens, it will take kind of the furthest sync that's happened so far and send all of the data that it hasn't sent yet up through that, if that makes sense. So basically, once these kind of acknowledgements come back, let's say they come back around here or something, then at this point, the code, each of these threads is kind of still parked, waiting for these offsets here. But at this point, once the acknowledgements come back, then it will send out both D and E over to the backups at the same time. And then kind of, you can imagine how the rest of it completes. So you basically get D and E here, D and E here, D and E here, and then once they're all there, it acknowledges, and then these two threads can return and tell the clients that the data has been durably stored. Does that make sense?
So does that mean that multiple writes from many clients all getting the same master roughly in the same time frame may get bashed if there's an outstanding sync RPC?
Yeah, exactly. So basically, if multiple clients are basically adding data to the head of the log at the same time, then the number of RPCs that goes out to the backups is strictly less than that number of writes. So it may aggregate multiple ones together, or it may not, depending on the timing. But yeah. Yep. Okay. All right. That seems good. All right. So I guess the next interesting thing is what you do when you roll over between log heads. So perhaps the naive way you might implement this is that every time the master rolls over to a new log head, you flush this data out to disk, and then that buffer is now empty, and so it begins to back up replicas from the same master. But that concentrates all of the backups, all of the master's data on a single set of 3 backups. As I said before, we want really high disk bandwidth when the node fails, and if we have all of the log data for a particular master stored on just 3 backups, it'll take minutes to get that data off disk. So what happens is along these segment boundaries, each time a master finishes filling a segment that's targeted towards one specific set of backups, once it fills that replica, then it chooses 3 new replicas at random from across the cluster. So over time, as it's adding data to its log, it's actually scattering that data across the cluster. And so that's kind of the whole key to fast recovery. And it's as simple as it sounds, except one thing, which is that the disk straggling is basically, if you have any disk that takes longer to read data than others during recovery, then recovery will be that much slower. So for example, if one disk takes twice as long to read data as another, then recovery will be 2 times slower than necessary if you had balanced the data across those particular nodes better. And so we want some kind of decentralized allocation policy like random selection, but at the same time we want to make sure that the data is very evenly balanced. So it turns out if you just uniformly scatter segments at random from across the entire cluster, that doesn't work so well. So basically, I guess what I'm saying is that once recovery starts, you kind of want all the disks to read ceaselessly at the maximum rate each of them is capable of, and then hopefully they kind of all stop reading at the exact same time. They almost all finish at the exact same time, because that's the maximum amount of disk bandwidth you can get from your entire cluster. Does that make sense? Okay. Okay. Right. So let's say the problem with scattering random, let's say uniformly randomly, Well, there's a few problems. Basically, one is failure modes. So we can't just replicate on every single, for a particular master, we can't just replicate on any of the backups. For example, a master can't replicate on its own backup. Certainly, that's not safe. And for example, we also don't want any of the backups to be in this, or the master's copy, or any of the backup copies to be in the same rack. And so just scattering uniformly randomly doesn't really take into account things like whether or not servers are in the same rack. So we'd like to compensate for that. There's also heterogeneity. So certain disks might have much better performance than other disks. You might have different disk models. You might have servers that have more disks than others. And you would like to balance according to the abilities of each of the machines. You want to balance utilization across the cluster. I guess disk utilization will probably get balanced well enough by scattering uniformly randomly. You want to accommodate additions and removals. So, for example, if you put a new host into the cluster and you're scattering things at uniform random, then that server that got added is going to be constantly behind. It's going to have less segments on it than others. And so over time, as servers crash, that means that it creates this imbalance, which hurts recovery time again. And also, it hurts the balance of disk utilization. So we'd like to compensate for that somehow. Let's see, what else? Those are most of the issues. The thing that's really helpful by scattering randomly, which is almost strictly necessary, is that we have to avoid centralization. So if you think about 10,000 servers, RAMCloud can write data pretty quickly. So at 10,000 servers, you can actually be allocating hundreds of thousands of log segments per second in the cluster and deallocating hundreds of thousands of log segments per second in the cluster. So that means we can't go to the coordinator and keep a centralized record of all this. So that's why randomization works out well. But, I forgot to put the most important issue, which is basically balancing disk read time. I guess that's kind of tied into heterogeneity in some ways. But basically, when you scatter, if you had equally performant disks, if you scatter at uniform random, let's say you have 8,000 segments on a single server, and you're scattering across 1,000 disks in the cluster, then each disk you'd ideally would have 8 segments, but in practice, basically the long tail, some of them will have more than double than that typically. Like with 80% probability, some of the servers will have 18 or more segments, which means that doubles recovery time because you got to wait for all those segments to come off disk. Okay, so basically what we do to combat that is we use Nitzenmacher's power of 2 choices, which you probably saw a few times at SOSP. And that gives us some of the benefits. Most of the benefits that randomization gives basically avoids centralization, but also balances things out better. So we do something slightly different. We basically do power of 2 choices is the real algorithm, but we basically do power of 5 choices. There are reasons for that. Basically, power of 2 choices doesn't balance quite as well as choosing. So what we do, basically, the algorithm, for what it's worth, by the way, I should describe that first, is you have a set of backups in the cluster, and all the masters know which backups are in the cluster. That's part of the cluster membership mechanism. So when backups first start up, they actually benchmark their disks. They report those benchmarks to the coordinator as they enlist. And the coordinator is actually streaming these updates of cluster membership out to the members of the cluster. And so the backups can easily, or the masters can easily keep a table that says the performance of each of the disks in the cluster, right? So you can say like 100 megabytes per second. This one has 200 megabytes per second, whatever. So what we do is when it's time to place a new replica in the cluster, we choose 5 candidates at uniform random from across the cluster. Here I'll just do 2. And the master is actually keeping track of how many replicas it's placed on each of these backups in the cluster already. And so basically multiplying this number by that number, it can kind of estimate how many seconds each of these particular disks is going to take to read its data during recovery. And so it chooses 5 of these candidates randomly from uniform random from across this list, and then it places it on the best, the one that will take the least time to read the set of segments when recovery actually happens. And so doing that balances the read time, which is the most important thing. It basically is within one segment of optimal for like 99.9% of simulations I think I ran.
How does it know which one is less busy?
Yes, so it's not globally less busy. You're trying to balance, so think about a particular master, right? The master is trying to balance, in the case of its untimely demise, that each of the disks spends the same amount of time reading. And that's only a local number that it needs to know. It needs to know how many replicas it placed there in the past. That's all it needs to know. It doesn't need to know anything about the other servers in the cluster. Right, it's just trying to balance its own segments evenly across the cluster. So.
I think you already mentioned this, but is a single segment, is every segment for a master sent to the same 3 backups, or every segment is sent to a different
Exactly,
3 backups?
right. And that's because we want that high aggregate disk bandwidth.
It's sent to
The second,
ones, right?
sent to different ones.
Right.
Basically, you want to scatter it, fan it across the entire cluster.
So you choose 5 and you get
You choose 5, so you have to pick 3 places, right? 3 places to put your segments. You pick 5, you choose the best one of that, and you repeat that 3 times. So yeah, it's slight. Yeah, that's why I said it the way I did, because I expect you to probably think what you were thinking.
Can you quantify how much of a difference it made to pick 5
Versus 2?
Rather than picking 2?
Yeah, it's basically if you pick 2, you are almost always 1 more segment off of optimal in terms of balance, and sometimes you're 2 more segments off of optimal. When you do, it's always 1 segment. It's almost always 1 segment worse than perfect.
Meaning one of your backups has an extra segment.
Yes. And so if you do the math on that and you assume that it takes 80 milliseconds to read a segment for disk, that means that 2 would add an extra 160 milliseconds to recovery time. So it's worth it, because in particular, choosing 5 doesn't cost us anything because it's a local data structure. It just takes a few hundred nanoseconds.
It depends on the number of machines in cluster, right?
Yeah, but I'm just assuming for like a cluster of 1,000, basically. So.
Oh, the simulation.
Yeah. And it's not like a globally true constant. Right. Sorry.
Is there anything that would make that number change over time? Is it possible that, I don't know, 10 years from now we want to pick 8 to get 2,
8.
or only 3 to get 2, or any ideas what would change that?
It feels like in a larger cluster, it probably doesn't matter. I mean, at some point you get down to the point where each server only has 1 segment or 0 anyways, and then I don't know. It seems like 5 would probably be always enough. It seems like when you scale down is when it starts to get, well, when you have better. I don't know. That's a good question. I don't know. It's a tough question to answer. Okay, let's see. Okay, so basically the advantages here. We have all the advantages of random scattering. So we avoid, we don't choose backups in lockstep. So there's no convoying or hotspots. There's no need for coordination. It balances out the disk read time. And one of the cool things too is, remember I said we want to bring servers kind of up in utilization who are new to the cluster. So if you think about this algorithm, if you have a number of 0 segments stored on you when you enter it, you're going to win the lottery frequently. So you're going to get chosen. If you're a candidate, you're going to get chosen. You're basically going to get chosen 5 times more frequently than the other servers in the cluster, right? And so that means you're not going to get a huge rush on you right off the bat where everybody chooses you all the time because you have the least segments and it just puts one after another on the same server. But at the same time, you get chosen more frequently than other nodes in the cluster until you get caught up.
In fact, won't you get a rush? So if the cluster is running fully maxed, so every backup is pushing stuff to disk as rapidly as it can, this new machine is going to get 5 times the load of anybody else, right? So it's going to be
5 times.
Trying to push 5 times as much as a disk
exactly.
can handle.
But it's 5 times. It's not like everybody consistently all collectively only chooses the new guy until it gets caught up. But
that means then something's going to have to give because masters are going to keep allocating more and more and more segments to it. It can't write them to disk as fast as new segments are coming in.
Right.
And so what happens then?
So in that case, we haven't implemented anything to handle this case, but we have the mechanism in place to do it. So backups actually have the ability to put back, basically to get themselves out of the equation. When a master asks to replicate a segment on a backup, it can reject that operation if, say, it's out of disk space, for example. But it could also do it if it's out of non-volatile storage space as well. So it can also do it, for example, if it's just overloaded. So it can just say, like, this is too much for now. I don't want to do this request. put it elsewhere. So that's another possible way to gate that. Yeah, which is something you'll need anyways. You don't want to adjust this constant backwards to try to reduce that load in some sense, because otherwise you start to affect the balance of your segments too, which is kind of an artifact. It has an extra artifact that's kind of annoying. It'd be better to let the backups gate this.
Just how long does it take to like flush a whole 64 gigabytes of memory to a disk with a current like disk?
I think it's like 2.5 minutes if you have 100 megabyte per second disk, right? So 64,000 over. It's basically for our stock disks it is. So
It's like 100 megabytes per second or
640 seconds. So
Great.
so yeah, so it takes a while. Our flash disks are substantially faster, but it's still not even close. So with 2 flash disks, I think we can do about 540 megabytes per
Why are
second
you
right now.
asking? There should never be a time when you can flush 64 gigabytes of disk.
Well, if that thing that you say happens, like there's a new machine in the cluster and everybody wants to
Right.
put data on it, so it could be the case.
That's why there's
You'll fill all
Right.
of the memory of that machine with that.
we don't allow that anyways. We basically we have a tunable constant right now. It's the naive implementation, but basically there's a tunable constant that says that a backup won't take more than X segments, buffer X segments at a time. So you set that low enough that you know it's less than your battery time. So you won't.
If you pass that entire amount, you basically can't back up anymore.
Well, for that backup will just turn you a request saying like try somewhere else. This is like you're putting too much pressure on me right
Can
now.
it be the case that everybody says?
Yeah, and then you'll get a lot of retries until they drain one to disk, and then you'll find an open slot, and it will put back pressure eventually on the client writes though. Yeah. Okay. All right. Well, so I think that's most of the interesting issues with segment scattering and how we provide the high aggregate disk bandwidth to recovery. Maybe the only other interesting trick about this is that everything I just described so far, you actually only need to do all this balancing for one replica of each segment. So during recovery, there are 3 replicas for every segment on disk, and you don't want to load them all because that would, you'd only get 1/3 of your disk bandwidth. So we tag one of these 3 replicas with a bit saying that it's a primary, which means that when the master crashes, those just automatically get read back from disk. And the expectation is that the recovery masters will be able to get the data from the primary replica. If they can't, then basically it'll fall back and it will load the redundant copies of the replica and on demand and load the data from there. But this keeps us from doing, getting a 1/3 of our disk bandwidth. It basically makes it so we only load 1 copy of each segment. And so the secondary copies aren't ever expected to be read, so we don't bother doing any of these balancing tricks that we do with the primaries. The secondaries are just scattered randomly.
Shouldn't you just balance the secondaries in terms of space utilization so you don't end up with, otherwise
Yeah.
you'll have to buy a lot more disk space than you need,
Yeah.
because otherwise some backups will run out of disk space.
But here we're making the assumption that balancing uniform random is good enough. So, but yeah, I don't know how the law of large numbers works out in that case, but.
We decided that uniform random would be off by a factor of 3 to 4. That's
So,
the worst case for one mass would have 3 to 4.
right, but the problem is that this mechanism isn't adequate for helping you balance disk utilization globally, is it?
With every individual master makes
I
sense
agree,
to
I agree.
across all the machines, then the
I
sum
agree.
of all those masters will also be uniform.
Yeah, so we could do that. We don't do that right now, though. Yeah, we don't do that. So right now
You've got all the information to do it.
we could, yeah. The secondary replicas aren't that way, though. Okay, that's a good point, though.
Another question.
So have you actually measured the performance cost of doing this instead of uniform random?
The performance costs.
In other words, like, how much extra time do you take to run this algorithm? versus
Sure.
doing uniform random?
Well, the thing is that this data structure is entirely in DRAM, so it's the cost of like tens of cache misses max. It can't be more than. It's certainly far less than RPC time. Far less.
So why would we have complicated the system by having 2 different mechanisms, one for primary, one for secondary?
I don't know. It's a great question. We could have done it still. I think we just didn't think it mattered at the time.
No, I mean, like, I thought normally if you don't think it matters, you go with a simpler approach. Which
It's an if statement, though. I mean, it's like it's one of those kinds of things. It's like think about this, for example. Like the core of the power of 5 choices technique is select one at uniform random. So the secondary one just says, so the primary versus secondary says primary, like loop through this and do it 5 times and take the least. The last one just says call that same thing once. So there's actually a function called select secondary, which picks one at uniform random. The select primary one calls that select secondary 5 times and just chooses the best of those. So.
And how often does this operation happen? Does it happen for every write?
No, yeah. So this.
Repeat the questions if you can.
Oh, I'm sorry. Yeah, I
Studio
completely spaced out about that. Sorry. For what it's worth, he's basically asking, why is there even this dichotomy to begin with? Wouldn't it have been simpler to code it up such that we always use the same code to select replica placement, which means we'd always do this power of 5 choices thing. So what was?
And then my question was, how often do you have to do this power of 5 things?
Right. So how often do you have to do this power of 5 choices thing? And the answer is you only have to do it once per segment. A segment's 8 megabytes. So in the worst case, that's once per every 8 objects, since the maximum object size is 1 megabyte. In practice, it's probably, if you have like 1K objects, it's much, much less often than that. So it's a rare operation. Anyways, okay. All right, I think that's the story for scattering, unless people have other questions about it. Then we'll talk about how we use these logs for recovery. Okay, I don't know if I need more space here. Oh man, this one? Okay, so there are a few interesting things about recovery. So the first thing I think is that, here, I'll write some stuff down here, although I'm not sure it's strictly necessary. So recovery, and we won't go into the details of recovery. Here I'm just talking about how do we find the log data that we've written, more or less. So one of the things that's interesting is you got to find them. So what I've described so far intentionally left out, well, you know, as I said before, we can't afford any centralized catalog of where these replicas are in the cluster. So how do you find them? Where are they? You know, where are they stored? So the answer to that is pretty simple. Actually, we just broadcast, and that sounds kind of heavy-handed, but in truth, as I said, we want all of the disks reading data during recovery anyways, and we know that the replicas must be on every server in the cluster. So we at least already have to send them a notification telling them, hey, server's crashed. You need to start reading data. So in that respect, we really can't avoid a broadcast anyways, and so basically, at the beginning of recovery, we send out a broadcast and ask every backup in the cluster saying, for this particular server idea, do you have any replicas that it left on your disk? And then the coordinator gets this list back and aggregates it together to figure out where all the replicas are in the cluster. So the next important question, though, is, well, do you have the whole list? Because some of the servers may have crashed in the meantime. And so how do you know that you're not missing some of the segments in the log? Well, so we're going to start this progression of problems and solutions here now. But basically, the way we do that is we make the log self-describing. We inject a catalog into the log saying, these are the segments that are part of the log. So we have a thing that we call a log digest, which I think Steve brought up last time probably to some degree. So what we do is when we create a new replica, basically our new segment, sorry, we stick a digest in there. So we'll say, you know, we'll stamp the front of it and say, you know, this is segment number, let's say this is segment 32, and then we'll put a list inside here and say, also, the log is now comprised of segment 7, segment 11, segment 12, and of course myself. And so each time we add a new segment to the head of the log, we can actually put a new catalog in there saying which set of replicas we need in order to have in order to ensure we have a complete log. And so when you broadcast to the backups, they look and pull this digest out and hand it back to the coordinator. The coordinator checks the digest, the most recent digest, against the list to make sure that the whole list is found.
Reading that most recent digest.
Yes, exactly. So, of course.
What
Sorry, go ahead.
every time?
Every time what? Sorry, I must have said something weird.
You said every time they send this list to the
When when a failure happens, yeah, basically, he's, I think, well, I'm not sure what the question is exactly. I think I just misexplained.
Well, you said every time the replica
Yes.
The most recent.
Right. And what I meant, so he's asking when is this digest sent to the coordinator? Because I made it sound like it happens randomly. What I meant is that during recovery, when they do this broadcast to find all of the replicas in the cluster, so at the start of recovery only, then it will get back the list, and it will pop out. Along with that, it will get back one of these from the most recently written replica in the log that contains a list of all of the other replicas. And then you just cross-check those to make sure they're all there. Which brings up John's very important point, which is, what if you've lost all the replicas for the most recent replica in the log? Well, now won't you just get back the log digest from the one that's one segment prior in the log, and then cross-check it and think that you have everything? And in practice, you've lost the most recently written replica.
But actually, before that, even if you didn't have any errors, how would you know what's the most recent mean?
Right.
All log segments look roughly the same, right?
Well, so the dumbest way to answer that is that the log segments are basically sequenced by segment ID. I think that's right.
So the
Yeah,
second
that's
highest ID is the most recent one?
is true-ish. Yeah, true enough for this conversation.
Truthy?
Yes. Okay. So right. So let's imagine we had a new segment 33 we added, right? And 33 has a different log digest in it. And then we lose all 3 copies of this. Well, now what happens? If we do recovery, do we find segment 32, use its digest, and then not realize we've lost all the objects that were stuck in here?
Isn't that log digest replicated 3 times? So
Yeah, but what if you lose all 3?
Oh, I see.
So now, will you silently recover to an inconsistent state and not even realize it? We want to make sure that never happens, right? Okay.
For example, the data center power outage, all the machines go down, and then the power comes back up, the coordinator reboots, and a few servers are there, but only a tiny number of them are there.
Right.
You want to delay your recovery until you give time for more servers to come up and supply you with all the data you need.
I see. Okay.
Yeah. Okay. So the way we do this is we basically, there are different ways to phrase this. I don't know what the best way is. We basically tag a replica to say whether or not it's the most recent. So it goes back to this idea of head. Remember here I was saying we've got all these segments in the log, but this one's the head. That's the one that's it's actively being worked on. So what we do is when we open a segment on the backups, we basically have a tag on here, a bit that says, hey, this thing's open. And then what happens is when you transition to a new log head, you open the next one, and then you scratch out the bit on this one. And so now if you crash and you find that there's nothing with the open bit set, you know you've lost data. You tell the user, I can't recover. I'm missing some segment. I don't know which one, but it's gone. But if you find one that's marked open, then you're in good shape. But this still raises one other kind of tricky situation, which is what if you mark this one as closed and then mark this one as open, but you crash before you finish marking this one as open, but you've already closed this one.
You should just do it in another order.
Right? But now you have a situation which is you can find 2 log digests.
They're open, but that's okay because you can see both their sequence numbers. You just take the max.
But what if the most recent one was lost still
Oh.
and it contained data?
Oh, I see.
All right, so now the final constraint that makes this all work. You're on the right track, so you're completely on the right track here. So basically what we do is we do what you described. So we have a rule that says, we call it open before close, basically. So open before close guarantees we'll find at least one open head segment when we recover, and if we haven't, we know we've lost data. But it means we could find 2 open segments, the 2 most recent ones at the head of the log. And the way we make that safe is, in case, what we do is we guarantee we never put data in this segment, actual objects in this segment, until this one's been marked as closed. So in that case, if you've either open segment would work. They might have different digests in them, but you know they cover the same set of objects in the cluster. Does that make sense? So we have a separate constraint called basically something like close old head before, I used to call it write, but basically append new data or something. It's the longest dash phrase ever. But basically it says, until you're sure that this digest can't be used during recovery, you can't put data in this segment. Once you have that guarantee, then you know it's safe to start adding data to this segment. So there's kind of this weird handoff in the head ownership. Who's the ground truth about what the contents of the log is? And once you make that safe transition, then you just kind of go on with appends as normal. Does that make sense? So all of this, just to recap too, is to make sure when we recover that, so we avoid basically having any centralized catalog, but at the same time we can tell if we've lost any data at recovery time. Okay. Sorry.
Three backups. Replica exists in the three backups, or even one big replica exists, it's okay.
As long as you're asking if, yeah, sorry. I don't quite follow it. You said if there's at least one, right? There's three backups, but if there's at least one what? Sorry.
Yeah, if as far as there is one existing replica exists, it's a byte for the do we require three replicas?
You mean?
As long as can the system operate as long as at least one replica is found for each segment.
Is that what you're asking? During recovery time?
Right.
Okay, so the question is basically how many replicas for a particular segment do you have, for each segment do you have to have before recovery can proceed? Is that the question? The answer is any of them works. And so we're not quite there yet, but that actually factors into a lot of the constraints on the types of how failures impact the log, because that means that you need to make sure that any replica that can be found during recovery will recover the log to an inconsistent state or that it's not used. Because any single copy is adequate. It creates kind of this danger that if there's an inconsistent replica and you inadvertently use that copy, then recovery will come to an inconsistent state. But yeah, the answer is any. And the reason for that is that we want to recover in the maximum set of scenarios as possible. So, okay. All right.
What's the overhead of your log digest?
It's less than 1%, and I think it's relatively unoptimized right now. Basically, it's a big set of 64-bit ints right now, but yeah.
This is for 64. Why don't you just do a quick back of the
I'm really bad at that, so I was hoping I could do it from memory. So
64 gigabytes.
there's 64 gigabytes. It's basically 8,000 segments that you divide the DRAM into. So 8,000 times 8 bytes each, that's 64 kilobytes. And so 64, 8 megabytes. 64 over 8 megabytes is about 1%. Does that make sense? About 1% of every segment is going to have this effectively wasted space in it. The only one that actually matters is the one in the head segment. The rest of them are dead. That's why the log cleaner actually immediately discards them if they're not the head. Basically, it doesn't clean head segments anyway, so it can, whenever it cleans the segment, it reclaims the digest immediately.
So it doesn't take up memory. It doesn't take up disk space
For too long.
It takes up until
Right.
the first time the segment gets cleaned, and then all extra overhead gets
Right.
swapped out.
This close old head before opening a hand.
Sorry, yeah. I just made that up on the fly, but
Is this a state for each digest, or just
it's kind of you're kind of getting at how I organize the replica manager in some sense. There are some state variables inside the master that keep track for each of the replicas whether or not each of these separate steps has happened. And there's like an interrelationship between each of the segments in the log that says before replica x plus 1 starts to do this operation, make sure that this bit is set in the state for replica x.
So there are like a couple of states you're always keeping for the replica, right?
Yeah, there's a lot of state, but those are just a couple of they're Boolean flags basically that say whether or not they've met this particular state.
Is this considerable overhead for these states to be changed?
Question.
Yeah, I see. He's asking how much overhead does it take to keep track of these states on the master. The answer is these are basically. I'm not 100% sure these are both bools. One of them might be kind of implicitly encoded some other variables, but basically it's 1 bit per each replica, and the replicas there's 24,000 replicas because there's only 24,000 bits. It's pretty small, right? There's basically 8,000 segments for a 64 gig server and 3 replicas each, so it's pretty compact. We actually have to keep more state than this, of course, right? So we have to keep track of several pieces of state in the replica manager just to give you a hint of how it works. But it basically has to keep track of how much data is ready to send, how much data has been acknowledged by the backups, how much data is outstanding, like how much is actively being replicated at the moment, and then so it has to keep track of several offsets actually for each replica at the same time as well, and then things like which server it's targeting, and it actually has to keep an RPC struct stored for each of these backups too, because it usually has an RPC outstanding each of them. So I don't know what the total state size is for the replica manager, but it keeps basically 24,000 of these structs at a time that it's juggling to make all this happen. Okay. All right, so I think that's pretty much it that I want to say about how recovery works. And then the recovery, the talk, will probably give you more of a sense of, well, now that we've found all these replicas and we're sure we have a copy of every single one of them, how do we squeeze them through the juicer to get our data back and reconstitute the hash table, etc. So that'll be a later talk. But this gives you a sense of how the log coheres together in as much as the replica manager cares. So the last thing, I guess, the last really important thing before we get to things like garbage collection. I have to use this space first. It's starting to get small. I think I'll move over here. We'll see. I don't know. This is going to be worse. It's going to be like problem solution for a bit here. But basically, I think one of the most interesting, well, it's a bit daunting, but I think it's actually interesting as well, is what do we do? How do we repair logs after failures? So this is kind of one of the last key pieces of what we need so far. So far we've talked about how we replicate it, how we get concurrency, how we get the data back, but then like the question is, well, what happens when the logs get damaged? Because they get damaged by failures. So I'll go through some scenarios here, and remember, so this gets back to Satoshi's point. Basically, we really want this read-any property where any replica for any particular segment will work so that we have kind of maximum recoverability. But that means we have to have pretty strong consistency between the replicas too. So one of the things that can happen that messes up your log is you have backup failures. Now, when a node crashes, you lose both a master and a backup. But now I'm kind of just considering, well, what are the consequences of the fact that you lost the backup component of a particular server? Well, in that case, you lose some replicas, right? And you basically have to recreate those replicas, or over time, those could accumulate into data loss. If you keep losing backups, eventually you're going to lose all the copies of some particular segment, particularly if one is kind of has a long shelf life. So basically, this works piggybacked on the, so before I talked about the mechanism that the servers use to discover backups and select backups. They actually use that same mechanism to find out when backups crash, because each of the servers in the cluster is getting cluster membership change notifications from the coordinator, and when a server crashes, basically the masters listen for those, and then they fire off when the kind of a crash event happens, they rip through all 24,000 of those replicas, and they check the server ID on each of them, the backup ID, to see if the backup or the server that just crashed was one that it had a replica stored on. So they just kind of check all their state real quick, and then if they see any state that says that this particular replica was on the backup that crashed, they just basically reset, they zero out that struct more or less. And then that replica kind of just starts over from square one and just begins to re-replicate like it had from the beginning. And it does that just from the DRAM of the master. There's no kind of like backup to backup re-replication or anything. All the replicas are always recreated using the master's DRAM copy of segments. Okay. So this raises a kind of a weird problem. So what if you crash while you're recreating a replica? So remember, we have some replica on the master. It looks all nice. It's got a bunch of data in it. It's almost full. And then we had some copies of this stored on a few backups in the cluster. I'll just draw two here. And we lost B2, and the master finds out about this and says, oh, I need to recreate a segment somewhere else in the cluster. So it begins recreating the segment on, say, B4 or whatever, and it starts filling it up, and then the master crashes. So now what happens when we perform recovery, right? We could recover using a copy of the segment, this segment using the one on B1, or we might use the one on B4. And if we use the one on B4, then we lose data. And we might do it silently if we're particularly unlucky. You can use like checksums and stuff to combat some of this, but if you get unlucky, you might actually recover to an inconsistent state. So the way we solve this is we make re-replication atomic. The segment that's on B4 will not become eligible for participation in recovery until it's in the final form that it should be. So what happens is there's a kind of an elegant mechanism, I think, for doing this that the masters use, but I won't go into detail about it too much. Conceptually, you can just think of it as a bit. When the backup recreates the replica, it kind of sets a invalid bit or something, you can think of it as, on the replica as it refills it. If it crashes at some point in the middle of recreating this, B4 will never get used because it's not really a valid replica for the segment yet. And then once it basically, with the final write that brings it into perfect consistency with the master's DRAM copy, it just atomically kills that bit off. And then that snaps into place as an eligible replica for that backup. So that helps a little bit. So let's do some more problems, I guess. All right, so we had a little outage there, I guess. We ran out of storage space or something because I was yammering too much. When we left, I was talking about backup failures and how when we're recreating replicas, we might be in the middle of recreating a replica. We might leave a busted replica, a partially recreated replica around, and how we do atomic replication to avoid that. So now I'm going to talk about a second problem that occurs because of backup failures. And this is called what I call lost head segment replicas. So remember, if you go back to this diagram, right, so I'll do a similar diagram to this. It's very similar. So there's basically a question about segment replica B2 here. So I showed you how B4 could have become an inconsistency, but actually B2 can be a threat as well. So now imagine this is a head segment. Here you could have thought this was a closed segment. Basically, they're all replicated up to about the same point. So here the master has some data, and it's actively adding data to the head of its log. It has some backup, B1, and it's sending out RPCs to replicate that data to it. B2, replicate up through here, and there's an RPC outstanding. It's supposed to append data to the head of the log, and then it crashes. We don't know whether that object got appended or not. It might not have. So the B2 may actually be kind of slightly out of date with B1. And then you turn around and we recreate the replica on B4, and we do it atomically, so we know we couldn't have lost any data, and we're all happy it's got that object at the head of its log. So now the problem is, well, what if B2 crashes and the system restarts? Well, if the system restarts and we effectively kind of take this X off of B2, right? And now the problem is if we've acknowledged this write to the client already, and then we recover and we find the copy on B2, now we're going to recover without that object again. So basically in the meantime, while the backup's been crashed, the state of that replica might have changed, and now we don't reflect those changes. So we basically have two real options. There's kind of two naive options. One is when you lose access to one of your replicas, you just freeze in place and say, oh, I can't contact it anymore. If I add data to my replica, I might be out of date. Well, that's no good because then we have availability issues when any of our backups crashes. And the second would be, well, why don't you just discard everything that's on the disks when you restart since you don't know whether it's consistent or not? Well, the problem with that is that you know that that there's a segment at the head of your log that's always actively being replicated. And so if there's a power outage, you're going to lose all of your backups at the same time. If you discard all of their disk state at the same time, you're just going to lose data as well. So there's got to be some balance where there's got to be some way we can allow most of the replicas on disk to be used during recovery, but we can detect when they've kind of become out of date with the most up-to-date copy of that particular segment. Does that make sense? And this is going to get hairy. So this will be the worst part. All right, so basically...
Close the segment at the offset.
Oh, man, don't do this to me.
And then move on to the next segment. That way you know all the replicas are valid and consistent. Even if B2 springs back to life, it's got the same data.
Such a long story. You probably have the answer already in mind, but I've already forgotten it. But we were planning to do that. one of the things we didn't like about that was that basically the replica manager would have to call back up into the log code and have it allocate a new head segment.
I think you also have a problem that V2 still thinks it's open. And if you've moved on.
Right. You can't clear the open bit on it.
You can't clear the open bit, right?
There's that. We had figured out a way to solve that, actually, for what it's worth. So we had figured out a way to do this. So there's some solution in that vicinity that works. But the problem is it creates this, it's kind of a locking issue. You have locks that the log is taking while it's appending stuff. It calls sync in replica manager, which takes some locks. And then you suddenly run into this situation in down here where you say, oh, shoot, there's an inconsistency, so I need to roll over the log head. Well, that's a log operation, so you have to make an up call. But now you got all these locks held while you're making this synchronous call. And so you got really complicated locking-wise. So we wanted we basically didn't want callbacks going back up the call stack. So that was part of the reason why, too. It was kind of an architectural reason to decouple the log from the replica manager a little better. So we have a scheme for doing this. And I'm going to draw a diagram. I hope it doesn't take too long to draw. I know that it's really boring when people spend a lot of time drawing, but I'll try to go fast. So basically, it's going to be another one of these diagrams where we have the master, a backup 1, a backup 2, and we'll have a backup 3 enter the picture. And this is kind of time working downwards here. So kind of in time sequence 1, you have the master's replica. And what we'll do is I'm going to add, John likes to call these epochs. I still don't really quite agree. I call them versions. So what we have is a version number on replicas, and you'll see this is the key to kind of shooting things down, to killing off basically these zombie out-of-date segments. So what happens is, I've already kind of given you the situation. You know, the master needs to append something to the head of its log. It does so. It sends it out to B1, which gets it. But this guy basically crashes in this old state. So, and in the meantime, basically, remember there's a write request kind of going on here, right? That's what's causing this data to kind of get added to the head of the in-memory log here. Is there's this pending write request waiting. Okay, so that's time step 2. Time step 1, time step 2. Time step 3 is, you've already seen this one, so we recreate the segment atomically. And one other thing is, I should say, what the master does is when there's a failure is it increments its log version number, which this is just the DRAM copy, so that's quite easy. It does the same thing when it sends a kind of a refresher RPC over to this guy saying you need to update the version number on this segment as well. So when you flush it to disk, it says 3 and not 2. And so, you know, this guy's still got the V2, so now you can kind of see how the solution's going to work. We're basically going to use a way to kill this thing off. So what we do is we recreate the replica, we do it atomically, we do it with V3. And this meantime, this write RPC is still outstanding, basically. It's all happening before we can acknowledge the client write. If we acknowledge it before that, we may recover using either of these 2 copies, in which case, if we had acknowledged a success to the client, we would recover to an inconsistent state. So there's a step right here, basically, which violates everything I've told you so far about scalability, where we send a number to the coordinator. And it says for this particular master M, the minimum log head version number is this version 3. So when recovery happens now, it knows that it should never use one of these stale replicas from version 2. And so in step 4, it's basically safe. I'll show you the kind of the ultimate failure scenario here and why it's safe. This is the situation you're trying to avoid, is when you crash this way. You don't want to lose all these and then this guy comes back to life. An improbable scenario, I know, but it needs to be correct nonetheless, right? So if these 3 guys crash and this guy comes back to life, now you see that his version stamp is 2, and so you don't recover using that copy of the segment, even though it's the only remaining copy. Does that make sense? I promise that's the worst it gets.
So every single write to that segment has an updated epoch number.
Exactly.
Okay.
Yeah, and I should say here at this point, you can acknowledge the write safely here. Once you've updated this epoch number on the coordinator, then the coordinator is guaranteed to throw out the stale replicas at recovery time, which means they're guaranteed, if you do recover, you will recover with that object, and therefore it's safe to acknowledge the write. So basically, during these types of failures, the master suspends all current operations, does this kind of refreshes all of its active segments, replicas, so that they're kind of more up to date to differentiate them from the stale guy, and then sends a request to the coordinator to shoot down the stale guy. And one of the kind of slick things about this is, so first of all, it's very low load on the coordinator, because as I said before, each node expects to have about 3 open replicas on it at any given moment, right? So when a backup crashes, there's only 3 masters whose head segments have been impacted. So we expect a server in a 10,000 node cluster, we expect like a crash every 15 minutes or so. So it means every 15 minutes or so, there's going to be 3 RPCs to the coordinator to update a single integer. So it's like a relatively cheap operation. So it's centralization, but only in like the most minor way, if that makes sense. Okay. Yeah.
Stuff isn't only happening when there is a write happening during a backup failure.
Exactly. Yeah. Well, we go through the same. Yeah, we actually do the same procedure regardless of whether there's a write open or not. If basically there'll basically be 3 RPCs to the coordinate, approximately 3 RPCs to the coordinate every time, whenever there's an open replica.
You don't know whether the master just crashed or the backup when the backup crashed. You don't know if anybody's actually actively doing the write at the time it crashed. That's hard to tell.
Right. The master knows what's been acknowledged by the backup though. But the problem is that it can't add more data to its replicas until that replica goes away anyway. So you really you have to do this regardless of whether it's right or not. Because the next write will cause it to become inconsistent almost immediately.
I think that the recovery of the backup failure with the duplication of backup takes a couple of minutes, right?
It does not actually. So that kind of gets back to the non-volatile buffer space that we there too. So we actually expect this will be faster than. This kind of depends. It kind of depends, but basically, if you imagine that it didn't have to contend for resources against master recovery, it does, because when a server fails, master and a backup crashes, and you have to do both either at the same time or serialize them in some way. So let's imagine you don't have to. What you have to do is a server had. A backup tends to have about 192 gigabytes of data on it if there's a 64 gigabyte master because it's the data is being triplicated. So that means when a backup crashes, the aggregate cluster is going to shuffle 192 gigabytes of data around. So it's actually better than master recovery, which has to shuffle that much data around, but also has to read another 64 gigabytes of data from disk. So we expect it to be in the 1 to 2 second intervals still, if there's enough non-volatile buffer space. But you have to contend with master recovery for that buffer space, so maybe. It depends. It depends on how big your non-volatile buffers can be.
I thought about this. What if you were to trigger the backup recovery, not on the crash event,
Right.
but on the removed event? You know, every
Right,
machine in the cluster
exactly.
is notified when a machine crashes, and then when the crash recovery is finished, and that it's ready time to get the machine out of the cluster completely, they get a separate remove event.
Right.
What if you waited to recover the backup data until that remove time?
Yeah, and I think the truth about that is you really can't finish faster than that anyways, in some sense. The only thing you're going to end up doing is probably slowing down recovery. So it seems like it's probably master recovery, sorry. So that's probably the better thing to do, I think. That means that you're going to have reduced durability for an extra 1 to 2 seconds, but it's fine. Yeah, I think that makes sense.
This is more of the comment you made about expecting crashing every 15 minutes.
Yeah.
I mean, if we're expecting crashing every 15 minutes, how can we guarantee any kind of latency? Because every 15 minutes during crash recovery, you're basically not responding to any requests.
For 1 to 2 seconds.
So every 15 minutes, you're going to be slow every 1 or 2 seconds.
I'd say it's pretty bad too, because actually the resource intensivity of recovery is so great that more or less your cluster is gonna seem really, really slow for that 1 to 2 seconds, effectively, nearly off. So basically every 15 minutes you're gonna see a performance spike of 1 to 2 seconds. Yep. In a cluster of 10,000 nodes though, which is a pretty big cluster too. So
And we expect to be,
you're talking about petabytes of DRAM there.
so it'd be a lot better for like a cluster 1,000 or 100.
You'll have less pauses then. Yeah. I don't know that whether that is You know, I don't know, when you think about this, the fraction of RPCs that tends to be still pretty low though. 1 to 2 seconds every 15 minutes. So it's like, it's still well less than, I mean, it's way under 1%. Yeah, it's 1 in 1,000, so it's like 0.1% that you won't meet your SLA. You could still meet 99.9% SLAs with low latency, right? But yeah, that's interesting. And we got the same comment of P talk was people. One of the questions I remember was like, you realize it's basically going to total your cluster for 1 to 2 seconds, and I was like, bring it on. We're going to do it so fast it doesn't matter. So, and definitely, I have to say, on the road, the talks I gave more on the industrial side, I got more pressure on that for what it's worth,
So
as to whether that's a realistic assumption or
It's only if you really care about your durability. If you, to some degree,
not.
huge question.
Yeah, he's asking, it's only true if you care about the durability of your data. So you could just restore the availability more quickly without restoring the redundancy, basically. There's some truth to that. I guess I probably shouldn't derail too much here, but recovery rewrites data to the logs of the recovery masters. So that's why there's 256 gigabytes worth of traffic for a 64 gigabyte master. In practice, the only thing you need to restore the availability is 64 gigabytes worth of traffic, right? Get the data back into DRAM. But the problem is that you need to set yourself up for another failure. You need to put yourself in a good state such that if another failure happens, you can recover quickly. And part of that is reorganizing the log in a way that you only have to read 64 gigabytes of data on the next failure. So it means you have to rewrite the data during recovery in order to repartition it according to the way you divide it amongst the recovery masters to ensure future recoveries are fast. So yes, you could get away with that for at least one hop. You could recover it wouldn't really increase your recovery time, improve your recovery times too much. It'd still be 1 to 2 seconds. But then, yeah, I don't know. So yeah, there are games you could probably play, but they wreak havoc on the complexity of managing the ownership of log segments and some things like that.
The bottom line is it takes 1 to 2 seconds to recover a master's data once it crashes.
Yeah.
It's crashing every 15 minutes.
Yeah.
That is what it is, right? We're not going to, unless we make recovery go a lot faster than that.
Yeah.
You can't get below 3 nines availability
Right.
with a 10,000 node cluster.
Okay. Well, I think you guys know. So I think those are all the. There's one other slightly interesting issue related to this consistency. It's not too big of a deal though. So earlier we were talking when backups become overloaded, kick back operations to the master and tell them, hey, I can't do that. I'm too overloaded. The one thing you gotta be careful about is backups can't decide to do that in the middle of re-replicating a segment. So if they just decide to unilaterally stop accepting replication requests from a master while it's in the middle of it, it'll create another one of these like partially created segments, and that'll create inconsistency as well. So what we do is backups can refuse segments for all sorts of overload reasons, but they have to do it up front in the very first request before they have the opportunity to become inconsistent with anything. So the master will send its first request to replicate a segment over to a backup, and it will say, no, I'm overloaded. If it doesn't say no and it accepts the write, then it has to accept all future writes to that replica. So it has to allocate all the resources up front to guarantee that it can always, that it won't just kind of quit writing in the middle. So that avoids a whole other set of inconsistencies that could happen. Yeah. And then I won't say too much about this, but basically there's replica corruption problems. So replicas come inconsistent because of gamma particles and things like that. And so the way we handle that is we have checksums on them. I won't say too much more about that, but they're basically computed on the masters and then stored by the backups, and the backups provide them back during recovery. The masters check them right before they put the data into a log to make sure that the data is still consistent with the way it was written initially.
Question about recoveries. What happens at the beginning of recovery? The coordinator goes around and talks to all the backups. They all send it their list of replicas.
Right.
And the coordinator determines it does not have enough replicas, does not have a complete log available to it.
Right. So in that case, I see. Sorry. I don't know why that's so hard to remember. So John's asking, when you lose all the copies of a particular segment, what does the coordinator do at the start of recovery? So it asks for the list from the cluster, and it gets the list back, and there's something, the digest names some replica that's just not in there. Well, in that case, basically it just aborts, and it queues up a follow-up recovery. So basically the coordinator is keeping a queue of servers that have crashed that it needs to process. So when a server fails, it pops it off the head of the queue, starts this broadcast, collects a list, performs recovery. If one of those is missing, it will just put it back onto the back of the list, and it'll just keep trying them round robin. So basically continuously do broadcasts to the cluster to see if it has a complete list yet. So if in the meantime a backup re-registers and comes online, and it brings along the right replica, the next broadcast will find it, and it'll eventually recover. Yeah, I was going to say something else about that too. Oh, and that also actually solves nicely another problem, which is what, and I guess this will, I'm kind of touching too much on recovery here, but basically if the same thing happens that John described, but not until the middle of recovery, so what if the coordinator collects the full list, it's all there, then it starts recovery, and by the time one of the recovery masters goes to replay the data, it's gone now? Same thing happens. The recovery master tries to get at any of the possible replicas it can. If it can't find anything, it just aborts, and then later on, the coordinator will reschedule a recovery for that chunk, and then it'll retry it later.
Who checks the checksum of each object?
So the checksums are a little bit wacky. I tried to gloss over that. So there's actually two types of checksums. There's a checksum on the replica, and the checksum on the replica actually covers the segment header, and it covers the log entries in there. And when I say log entries, I mean just the piece of the log entries that describes what the type of the entry is and how long it is. And the reason is because if those are corrupted and we try to walk the segment, we could jump off the end of the segment or do something insane. So we want to make sure that thing has integrity before we try to walk the structure. Now the individual objects, as far as the backup cares, it doesn't care if those are corrupted or not. It'll feed those back to the recovery master. So those actually have a checksum. Each of those have their own independent checksums on them. And when the recovery master goes to replay each object, it checks the checksum on each individual object. So there's kind of two types, one on the object and one on the replica itself. But the one on the replica itself just kind of covers the replica metadata frame. And then the same thing kind of happens that John described. If the checksum doesn't match when the recovery master goes to do replay, it just kicks back off and tries to find the object in a different copy of that same segment. Okay. All right, so that's about replica garbage, corruption and consistency and all that good stuff. The last thing we have to talk about is reclaiming replica storage. I won't go into too much detail here. There's a few kind of weird twists and stuff, but I don't think they're actually all that exciting for the most part. A lot of them are just kind of very artifactual. But there are a few interesting things, I guess. So basically, I already told you before that whenever the log cleaner decides to reclaim storage, the disk cleaner decides to reclaim a particular replica, it sends it calls this free method on the segment, and that sends an RPC out to the backups telling them to release the storage space. So that's all fine. The kind of trickier issue is, well, what happens if the backup has there's a couple different scenarios. Kind of like, what if what about the replicas that are left behind when the master crashes? So it's not going to be sending any free RPCs out after it's dead, right? So what do we do? What's that? When the master crashes, actually. Maybe this just seems like it's an obvious solution, but basically when a master crashes, you need all of its segments for a very brief window, and then once recovery is done, they're garbage. And so the way that works is it uses that cluster, the coordinator's server list tracking mechanism I described again earlier. So the backups are basically listening to these broadcasts from the coordinator, and when they see that a particular server has been removed from the cluster, when they see it's crashed, they hold the replicas. They don't do anything weird with them. But then when they see the event coming saying that it's been removed, that means that those replicas will never be needed again because the data must have been recovered elsewhere. And so they just delete all the segments and reuse the storage space. So then the point comes up that John mentioned, which is, well, what if a backup crashes and then restarts and it finds a bunch of replicas on its disk? Well, in the meantime, the master's moved on with life, probably recreated replicas elsewhere. It's forgotten about the fact that it ever even put replicas on this particular backup. And so we need to kind of look at each of the replicas on the disk and decide whether or not we want to keep it or throw it away. If the server's still up, we may need to keep it if it hasn't re-replicated the data elsewhere yet, but if it has, then get rid of it. If the server is down, we can get rid of it. If the server is crashed and we're in the middle of recovery, we sure as heck better keep it. And so this is all predicated again on that server list. So basically, if it's crashed, keep it. It's kind of the algorithm. When you start up, you check each of them. If it's crashed, keep it. If it's been removed from the cluster, discard it. If it's up, well, now we got to find out whether the master's recreated the replica or not if we want maximum durability, because it might be the case that that master is about to crash. It hasn't re-replicated it elsewhere yet, and we want to actually keep that to make sure that we can recover. And so the way we do this is basically the masters, the backups for servers that are still up and for which it has replicas, it asks the master. It says, like, do you still need this replica? The master just looks through its list to see if any of the server IDs match the former backup ID that that server is operating on. So the backup basically provides it and says, hey, I'm server 32. I used to be operating as backup number 16. Do you have 16 listed amongst any of your replicas? Because if you do, or for this particular replica, because if you do, I have this copy of it, and I want to discard it, but I don't want to discard it if you still think you have it replicated on me. So if it still believes that it needs that replica on the backup, it'll say, okay, we'll just hang on to it for a second and ask me again later. And then the master will eventually find out that that old backup 16 crashed and re-replicated elsewhere, in which case, when the backup requeries about that segment, it will find out that it's been re-replicated elsewhere and discard it. So that's most of the trickiness there. There's one really annoying aspect to that algorithm I just described, which is that I don't think I'm going to really dig into the detail. Should I really dig into it? It's probably not worth it. So basically, the one thing you got to be sure of is that the master needs to be sure, when you ask a master whether it needs to keep a particular replica or not, you need to know whether or not it's processed the backup failure. Yeah, I don't know if I want to describe it or not. It's basically there's an ordering constraint you have to ensure of. When a backup re-enlists with a cluster and finds some replicas on its storage, and it asks a particular master whether it should keep a particular replica or not, the only way the master knows the correct answer to that question is if it's already processed the failure of the backup that's asking it that question. Well, unfortunately, our server IDs change every time you re-enlist, and so you can't, a backup 32 can't just ask and say, hey, I'm 32, do you have any replicas for 32? The master will say, I don't, of course not. So you need to make sure that it already has found out that 16 has crashed before it can accurately answer the question whether or not it should discard or keep the replica. So we have to create some kind of bizarre ordering between the failure notifications to make sure that the failure of a backup, when a process crashes and restarts on a particular server, that those failures are processed in order on the master. And so we basically use some tricks in the enlistment mechanism to make sure that these orderings happen and that the masters don't inadvertently say throw away a replica when they haven't even actually found out that that particular backup had crashed yet. So I won't bore you with too much more of that. I think it's adequate. Yeah, no, it gets worse than that. I mean, it's close, but yeah. I think I did it in a way that no one could have understood, but at least you might have a flavor for it. Other questions about this stuff? To give a brief summary of kind of what I've said so far, maybe. So basically, Steve talked about how we organize data on a single master. And the kind of distributed part of that is what I was talking about today, which is how we go from the copy that's in the master to copies on disk, and how do we reuse those later. So I guess kind of the key interesting aspects of that were that we kind of replicate the data into these non-volatile buffers, which allows us to do fast replication without high seek times from disks. And we scattered segments across the entire cluster so that we have very high read bandwidth during recovery. That's a very important property. And I think maybe another interesting aspect is that we have this kind of decentralized way of verifying whether or not we have the integrity for the log, which allows us to have kind of very high throughput without putting a lot of load on our coordinator, which is a great property. And but we still have this cool property, which is you can pretty much use any replica at any time in order to recover. So it's very easy. It's very likely you'll be able to recover, even if there are failures when we lose some of the replicas. And that's mostly it. So then there's some tricks about some kind of edge cases where you have to make sure that you're careful about how you repair logs after failure, so you don't end up with partial segments that are missing some objects. And I think that's mostly it. Okay. Any other questions?
Great.
Thanks, guys.